Because I record this Meet when I record your asynchronous lectures, and I use it from this particular link from the calendar, it shows up in your calendar. So remember how I said that you can always access the videos from our class either using the YouTube link that I post on D2L, or you can access it through a Google Drive link through the calendar. Well, I didn't realize that you could also do the same for our asynchronous lectures. So if for some reason you cannot find the YouTube link, I don't know why that would ever be an issue. Or I had this happen, okay, not every once in a while. I'm going to say it happened one time that YouTube was down and the class couldn't watch the asynchronous lecture. I don't think it was down for more than maybe like an hour or two, but still it was at a really bad time. But both of the week's lectures should be saved in the calendar entry for that week. So like on September 1st, I'm seeing 2 different Google Drive video links. One of them for the asynchronous, which I recorded the previous week, and then the other one for September 1st. So anyway, just wanted to mention that because I saw it tonight and thought it was an interesting thing to note. So if you see 2 links in there, I don't know, most people probably watch the YouTube links, but if you're watching the Google Drive links that you access through the calendar and you see 2 different ones, you can hover over them. They'll tell you what date I recorded it and what time. It's very specific. Okay, I'm going to wrap up chapter 6 tonight. I've had to sort of change the way I teach this slightly just because of the fact that I only see you once a week and there are certain things I don't want to do asynchronously. But this is the amount of time I normally spend on chapter 6. So by the time you take your test, we will have spent 4 weeks doing chapter 6. That's very much the exact same amount of time I always spend on it. For the 17-week semester, we have 4 chapters to cover. That's how long we can expect to spend on each chapter. Some chapters are longer than others, but this one's about medium length. So I'm going to wrap up chapter 6 tonight, like in this class. Now, this is excellent news for you. And you might be thinking, like, this is terrible news because now we'll have asynchronous work over chapter 7. No, that's not what I'm going to be doing. And I was looking through the schedule that I put out for you in the syllabus. And our schedule, and we are right on schedule, says that your first test is supposed to be on September 15th, which is a week from today. We're totally on time for that. And it says that we're supposed to work on 6.5 and 6.6 for the rest of this week. And your asynchronous stuff, remember, always corresponds to the following Monday. And that would be covering 6.6. Now, I really feel like I'm going to finish all of 6.6 tonight. If for some reason I don't, I will record an asynchronous example, but I can't see it being like more than one example. So what I'm going to do, instead of having an asynchronous video, and hopefully this will work out really well for you, is I'm just going to include an additional student hour for you to ask questions. Now, I know that we all have different schedules. And I'm going to have to set an alarm so that I remember to show up to the student hour that I'm going to pop in here. But in lieu of the asynchronous lecture that I would normally release on Fridays, in lieu of async lecture released on Friday, I'm just going to offer some review time for you, for me to be available for you. I feel like that would be more helpful than you just continuing to watch me do more examples. And like I said, I don't really have much more to do. I did not want to finish this chapter asynchronously, which is kind of why I worked it out the way that I did so that we started 6.5 last time. So you maybe had a little bit more work to do than I would have planned last week, but you're going to have less work to do this week. I also know that a lot of you really need to catch up, like severely. So the last thing I want to do is throw even more work at you over the weekend. So in lieu of an asynchronous lecture that I would normally be releasing on a Friday, I'm just gonna put in some office hour time. If you would like, I can record the office hour. I will definitely be posting any notes from the office hour. I'm gonna plan for that to be at, let's say, oh shoot, my son has piano Friday. I'm gonna email you. How do we feel about Friday? Does Friday work for people, or Saturday I cannot do this week? I could do Sunday. I could even do Monday. But Monday you already have an office hour, so that would be kind of pointless. I could also send out an email survey and ask what dates people would be most available, whether it be Friday or Sunday. It would be one or the other. I just have to take my son to piano Friday, 4:30. And my kids are up at 3, so I can't do it at 3. Technically, no, and I have to pick them up from the bus. And there's no other time to do it. Let me think about this. I might have to do the hour on Sunday. But in lieu of the asynchronous lecture that I would normally be releasing on Friday, I'm going to give additional student hour time. For catch up. Now, let's say I schedule the student hour time and you are like, oh, I can't make it. I have something else going on. Just email me the questions that you had that you wanted me to address. If you want, even request that I record the student hours and I'll record it, but definitely I will post the notes on D2L. I don't want you to feel like, oh my gosh, I have to be there, or like I wanted to be there and I couldn't make it. Just, I will cover whatever questions you have. Just send me an email. And that's not a big deal. And we'll see what time I can do Friday or Sunday. Friday or Sunday. Friday will be trickier. Sunday is a possibility. But I'll send an email. And then Monday, I will still have my regular office hour Monday, which is at 5 o'clock. So from 5 to 6 on Monday, I'll be my office hour as usual at this link. And then you will have your test, which is on chapter 6, whatever we covered from chapter 6, which in our class will be 6.1 through 6.5. Or I'm sorry, 6.6, not 6.5. That will be on Wednesday, 9:15. Now, that's in lieu of our normal class time, and that's because I need you all here synchronously. I'll be proctoring the exam. I'm going to send out an email at some point this weekend with instructions. I've had half of you before, so you know what the instructions are for taking asynchronous tests in my class, but I'm going to make sure that everyone is aware of the camera angle they need, what resources they have available to them, where they're supposed to upload their tests, how they're going to receive their tests. It's going to be a long email, but it's going to have all the pertinent information in it. We'll send email with testing instructions over the weekend, just so that you can prepare and you know exactly what you need. But your test is going to be during class 6 to 8:20. You'll have the full time, including the break time, 6 to 8:20 on Wednesday, the 15th, which is a week from today, covering chapter 6. So if you were one of those people who kind of got off to a slow start, you need to catch up. This hopefully will get everybody where they need to be. Email me any questions that you would like for me to cover in the additional student hour. Otherwise, I'll still have my student office hour on Monday from 5 to 6. So no asynchronous work this weekend. If we had a Monday, Wednesday class, I would have tested you Monday, but that's not the way it is. So we kind of just work it out this way. And then we'll start chapter 7 right when we're supposed to on chapter 7 you'll start asynchronously then. Yeah, so you'll have test 1 Wednesday, and then available to you probably even as early as Thursday morning, since it's the beginning of the chapter and I don't have to worry about where to pick up. You'll have the 7-1 lecture available to you to start, and then be ready for 7-2 then in class on the 22nd. I'm going to add that to my notes. Start 7-1 asynchronously as early as 9:16. Be ready for 7-2 in class on 9:22. I just said 22, but it seemed really weird. Okay. 22. September is going to be over before you know it. Okay. That's my plan. I feel like this weird format that we're in is causing me to do all kinds of crazy things. We got an email from the dean that supposedly next semester they're going to do as many classes as absolutely possible in person. Keeping my fingers crossed. Any questions of the schedule?
As for going over the quiz, can we also do question 3 and might as well throw in 1 since someone asked for 2?
Okay. Yes, let's go over the quiz. Quiz 2. Number 1. Here's my quiz.
Oh, and somebody asked if there was a review on Achieve for the chapter 6.
Oh, yes. I'm glad you asked. Oh, I looked today, and one of the things that I wrote in my little WebAssign review was how awesome it was that they correlated review problems for you guys to do from the book. So I look in Achieve today, and they have like 10 that are available, and like only half of them really are things that I would feel would be good for you to do. So I'm going to have to make my own review assignment. But yes, I will put a review assignment on Achieve for you, because I do think, especially if you missed the homework, like if you just didn't get a chance to get it done, I don't think Achieve lets you in it afterwards. And I mean, do they let you in, but they just don't grade you on anything? Or do they just not let you in?
You can't do the problem and see if it's
Can't
right.
do that. Okay. I'm wondering, 'cause a lot of times I want students to be able to practice them, but I also don't want to keep giving credit for them. I wonder if I could switch up the homework settings to at least allow you to see them, but if not, I'm going to create a review assignment for chapter 6. I'm going to do that hopefully tonight. Chapter 6 on Achieve. Yes, I'm glad you asked that. Okay, PLC is coming on. The nice thing is I'm at home, so if PLC is coming on, I don't have to feel like I'm a social pariah. All right, so for the quiz, question 1 was for the region bounded by y equals the square root of x minus 2, y equals 0, and x equals 4. Use the shell method to choose the correct setup to find the volume when the region is revolved about the y-axis. All right, so this is the square root of x shifted to the right 2 units. Because the minus 2 is inside the function. Y equals 0 is the x-axis, and then x equals 4 is right here. So there's your region, and we're revolving this about the y-axis. Okay. Now, notice that if you were to use a washer, this would be a much harder problem because you would end up not only needing to use a washer where you would need an inner and an outer radius, but you would also have to talk about this function in terms of x instead of y, which is always harder for us to do. But using the shell, we're going to draw a rectangle parallel to the axis of revolution. And when I need a shell, that's a much easier situation generally if I'm dealing with what would have been a washer. Now, as long as I'm revolving about the y-axis, I can say that my p of x is x. And remember, you can always check this, but your rectangle is x units away from the axis of revolution. Remember, you can check this by moving your rectangle to the right of your region and to the left of your region. So if I moved it all the way to the right, well, then x would be 4, and I would be indeed 4 units away from the axis of revolution. If I moved my rectangle all the way to the left corner of this region, x would be 2, and p of x would be 2, because it's x. So I'd be 2 units away, which you can see is the case. So p of x is x, and h of x, the height of your rectangle, is going to be top minus bottom, which is the square root of x minus 2 and then minus 0. So you don't need to really think about, I mean, a lot of you will just think about the height as being the function value, and you're not going to be subtracting 0 from it, and that's fine. But these are your p and your h. So now when you go to set up your integral, remember that for a shell, we're looking at 2 pi instead of 1 pi. And we'll multiply by the integral from, we're looking at x, remember. We're only going to look at where the region lies on the x-axis. So I'm not going to go from 0 to 4. Why didn't I put that in as a distractor? It would have been so good. I don't know. I didn't think to do that for some reason. You're going to go from 2 to 4 because that's where our region lies on the x-axis. And then we'll take p of x times h of x dx. Now, I only asked you for the setup in this case. I did not ask you to actually solve this integral. If you did, this would be an instance where you would need to use one of those change of variable deals, because u would be x minus 2, du would be dx, and you would then need to create this x by saying x is u plus 2. But I did not ask you to do that, so you don't need to worry about that. Okay. Wonderful. Any questions on number 1? Okay. Excellent. Number 2. I told my husband last week that I could hear him mowing the lawn outside and it was really distracting. He was like, really? I'm surprised by that, huh? And guess who's out there mowing the lawn again? Right. See, this is where he's like, really? My wife is getting mad that I'm mowing the lawn? It's the timing. Set up an integral to find the volume of a solid whose base is the semicircle y equals the square root of 9 minus x squared. And we're looking at x between -3 and 3. The cross sections perpendicular to the x-axis are squares. So if you're thinking about this function, I mean, you could graph this on Desmos. If you put this into your graphing calculator, if you didn't square out your viewing angle, then this would not look like a circle. It would look like the top half of like an ellipse or something. But remember that this is just a circle. If you were to square both sides, you would get x squared plus y squared equals 9. So this is the circle that is centered at 0, 0 with radius 3. So that's what your circle would look like. However, remember that this is not a function. The y equals just the positive square root of 9 minus x squared indicates that we're only looking at the top half of the circle. So that's why the instructions stated that we were looking at this function, which was a semicircle. So this is your function y equals the square root of 9 minus x squared. Desmos should have that squared out for you. Your calculator window is not square unless you make it be. All right, so this is your region. Now we're going to look at this in 3 dimensions. Okay, so here's your semicircle. That's x is -3, x is +3. Remember, it comes towards you. And then also through y is 3. So, you know, it's not going to look perfect because it's in 3 dimensions and you're human and you can only, it's always going to look funny regardless, but you can get a sense for what this looks like if you were to sort of view this from a different perspective. But here's your region. And you were given the information that this graph goes from x equals -3 to +3, which it must anyway. The squares are perpendicular to the x-axis. So that means that when you draw your squares, they're going to be parallel in this case to the y-axis. So one square might have a base that looks like this, and do the best you can to make this look like a square. Maybe something like that. Close. My lines are a little bit off, but you do the best you can. And now you can draw another one if you want to. You don't have to. If you're trying to get a sense for what this region looks like, you might want to draw more. If you're just trying to, if you're one of those people who just needs to think about things in terms of formulas, then maybe it's enough for you to just sort of figure out exactly what the base is. But notice, if we're talking about squares, remember that the area of a square is just the base squared because the base is the same length as the height. So if you already know that the base is based off of this length, the square root of 9 minus x squared, then we can go ahead and say that the base is the square root of 9 minus x squared. And now to find the area for a square, we just need to take the base and square it. So our function a of x would be the square root of 9 minus x squared, which would just be 9 minus x squared. So I think if you're struggling with this at all, it's probably just with understanding that the length of the base is just based off of this function value. Now, sometimes I think this is harder to see in 3 dimensions if you're just thinking about this in terms of the length of this base. So if you need to, go back to what this would look like if you're looking at it straight on in 2 dimensions. So imagine that you were sitting on the z-axis and looking down towards y and x, and what you would see would look like this, and perpendicular to the x-axis is where your bases for your squares would lie, somewhere in there. And now you can see that the base length for your squares would just be whatever the height would be at that point, and the height is controlled by the function value. So the base of your square is always just going to be the square root of 9 minus x squared, because that'll just give you the y value, which will give you the height of that line. And then once you have that, and you know that this figure also continues in the back, but you're going to see that because these two, the base and the height are the same, you're going to end up getting, again, the same circular behavior as you head up and then back down again. So a little bit hard to see, but we've seen a lot worse than that. But there's your area that we're basing everything off of. And then you're going to go from -3 to 3. And that's because we're including this whole piece here. So when you're drawing your squares, you've got bases that go all the way from -3 to +3. I didn't draw them in 3 dimensions just because it's going to end up looking really cluttered. But you're also drawing squares all the way back. So you're going from -3 to +3, and then you're taking your area function, dx. Questions about that? Oh, and by the way, one of your distractors, I only took from 0 to 3 just to see if you're paying attention to where the beginning values started for your region. And then for another distractor, I just multiplied it by √3/4, just thinking that like maybe you would take the base and like treat it like an equilateral triangle and then take half of it. I don't know. Just threw it in there. Questions on 2? Okay, so the last one was the arc length one. Number 3. So this was find the arc length. This is really just sort of, can you follow the formula? And we'll go from 0 to 9. So remember when you're finding arc length, you'll take y prime. And the derivative of 1 is 0. So this is 3 times the square root of x, and then you'll square it. I think one of the distractors I based off the thought that maybe you would square the square root of x and forget to square the 3. I don't know. I just try to come up with things that maybe make sense. And then you'll take y prime squared plus 1 to get 9x plus 1. And now for the arc length, you are going to take the integral from 0 to 9, since your interval is going from 0 to 9. And remember, you're taking the square root of y prime squared plus 1. Now, because your radicand is linear, you can work on this integral without having to worry about missing anything out here. Just use the u substitution. And you'll get u equals 9x plus 1, du equals 9 dx. And then 1/9 du is dx. I would switch my upper and lower limits of integration. It's up to you. You don't have to, but it will make your life a little bit easier in the end. If we know that u is 9x plus 1, if x is 0, then u is just 9 times 0 plus 1. And if x is 9, we get u equals 9 times 9 plus 1, which is 82. And we will set up this integral from 1 to 82, 1/9 u to the 1/2 du. To 1/9 times 2/3 u to the 3/2 from 1 to 82, which gives you 2/27 times 82 to the 3/2 minus 1. So that was your quiz.
So when you were getting the derivative, do you not get the derivative of the 1? Shouldn't that remove it?
Yeah, so when I took the derivative of 1, I got 0, so I just didn't write it.
Yeah, but then you added it back on at the end. What was that for?
Yeah, that's from the formula. So remember your formula for arc length is always the integral from a to b of the square root of f prime of x squared plus 1 dx. You always add 1 to the square.
Oh, it's from that. Okay. Yeah.
Always, yeah. So this was unrelated. Yes, but I can see how that's confusing. Other questions there? One of the nice things for you guys about Achieve is that they haven't covered as many questions, so there are fewer homework problems that I like that are available to assign. And at first I was kind of annoyed by that because I was just like, oh, really, it doesn't seem like I'm assigning as much as I normally would. But honestly, if you can do those problems that I put in there, even if there are only 4 of them, I feel like you have a good sense of what you're doing. So even though there are 10 of them, maybe less can be more in this chapter. Okay. That was what I was going to say about the quiz. I have one example that I want to show you from 6.5 that covers a topic about surface area. Your book doesn't do a whole lot with surface area, so I'm not going to ask you to do a whole lot because I'm not writing custom homework questions for you. Let me get my book open here so I can give you a definition. The whole office hour, I couldn't find my calculator, and while you guys were taking your quiz, I just found it behind. It was just sitting innocently behind this giant stack of notes and books that I have here. It's just a lot of things. Okay. So last time we talked about 6.5 arc length. I'm just going to quickly talk about surface area. There's not a whole lot to do with surface area, and the formula is pretty similar to the one that we used for arc length. There's just a little bit of a difference there. There's a reason we put these in the same section together. So here's your theorem. Surface area of a solid of revolution so we've talked about volume, we've talked about area, we've talked about arc length. Surface area is really this last geometric piece that we're including here with all these applications that we're doing with integration. Suppose a function y equals f of x is non-negative and continuous. On the closed interval from a to b. And has a derivative that is continuous in an interval containing a and b. The surface area. Now, normally we denote arc length with a lowercase s and surface area with an uppercase s. I'm going to try to make my s look uppercase there. Of the solid of revolution obtained by revolving the region bounded by the graph of the surface area S of the solid obtained by revolving the region bounded by the graph of f of x the x-axis and the lines x equals a and x equals b about the x-axis is given by, I know that's such a huge long definition. We haven't had a whole ton of huge long definitions. in this class so far. Oh, you'll see a lot of them as we move ourselves into chapter 8. Okay, here's your formula. The surface area. This time you're going to multiply by 2 pi. You're going to take the integral from a to b, and everything after this is going to look the same as arc length, except that you're going to multiply inside your integral by f of x. But you're still going to take f prime of x, square it, and add 1 to it. So this is your formula for surface area. So I'm going to use this formula to go over an example of surface area with you. There aren't going to be very many homework questions at all. There might be like 2 or 3. I have to assign it, so I didn't see what was in there to choose from. But I'll go over an example with you that's kind of similar to one that your book has in it. Oh, I wish I would have looked, because what this example that is similar is the only one that's available. Yeah. I should have done another one. We'll find out. How long does it take to mow the lawn? We don't have a big yard. I'm going to call this, I'll just call it example 1, even though we technically already started 6.5. So we are going to find the surface area. Give you your exact instructions here. You're going to be asked to find the surface area of the solid. Formed by revolving the region bounded by, we will do y equals 3 times the square root of 2x the x-axis and x equals 1. Let's go from the 3. About the x-axis. So we're going to use this formula to find the surface area. Just like we did with arc length, the first thing you want to do is take the derivative, then you're going to square it, then you're going to add 1, then you're going to take the square root, then in this case you're going to multiply it by the function, which in our case is 3 times the square root of 2x. So we're going to use this function twice as we work our way through here. All right, so we're going to take the derivative. So if we originally have y equals 3 times the square root of 2x, and note, by the way, that the quantity 2x is under the radical. When you take this derivative, you will probably want to rewrite this. Now, how you do this is kind of up to you. I'm going to use the chain rule to rewrite it, or to take the derivative. So I'm just going to write this as 2x, like the quantity to the 1/2 power. I guess you could actually just split that radical up into the square root of 2 times the square root of x, and you wouldn't need the chain rule. But sometimes I think it's really good for us to practice the chain rule because we don't see it all the time anymore like we used to. Whatever you do, don't multiply the 3 by the 2. Remember, this is not really 2. This is 2 to the 1/2 power. So you can't multiply this in here. You're going to have to leave it the way it is right now. So let's go ahead and take the derivative. The 3 can stay right where it is. We're going to use the chain rule here. So we're going to bring the power out front. We're going to rewrite the inside function. We're going to decrease the power by 1. And don't forget, when you use the chain rule, you're multiplying on the derivative of the inside function. So the derivative of 2x is 2. That's why we multiplied it here. And if you're kind of looking ahead, you can see that the 1/2 and the 2 multiply together to give you 1. So we can rewrite this as 3 divided by the square root of the quantity 2x. Now we're going to take that derivative, and we're going to square it, and we're going to add 1 to it. So hopefully if you got, I know the 6-5 homework wasn't actually due yet, it's due Friday, but if you got to that already, you should be in the habit of doing this by now. So y prime squared is going to be 3 divided by the square root of 2x, and you're going to square that whole quantity. So in the numerator, you'll have 3 squared, which is 9. In the denominator, the square root of 2x squared gives you 2x. And then the next step is to add 1. Now, I know this seems so trivial because you're like, okay, fine, add 1, big deal. You would be surprised how this will screw up your integral depending on how you write it. Now, if you want, we can put this in the integral and then rewrite it, and you can kind of see, because I don't want you to be like, well, how would I have known to do this, or how would I have known to do that? I get that question a lot from students. So I'm going to leave this right here for now, because sometimes we just don't know until we get there. But let's go ahead and set up our integral. So the surface area is going to be 2 pi times the integral from, and we're going from 1 to 3. So this is written slightly differently with arc length. I would give you a closed interval and say like 1 to 3. But in this case, we're just talking about these radial lines. And then we're going to take the function and put it in front of the radicand. So my function is 3 times the square root of 2x. And then behind that, this is where we're putting the square root of y prime squared plus 1, which is 9 over 2x plus 1 dx. So we're going to integrate this. I'm going to get on to my next page here. If you'd like, if this 3 is bothering you and you don't want it inside your integral anymore, you can always pull that out and multiply it by the 2. It does bug me, so I'm just going to multiply that out, going from 1 to 3. And then I have the square root of 2x. Now, what you should be noticing here is that there's really not a whole lot you can do with this integral if you leave this in this form. What we're trying to do here is get in some sort of integrand that we can work with. So what you need to do, and I think I did one like this when I was talking about arc length, is you're going to rewrite this as 1 fraction. And to do that, you're going to rewrite 1 as 2x over 2x. So this will be 9 over 2x plus 2x over 2x. Because what we're going to do is we're going to combine these, and then we're going to get this split into, instead of the radical of a quotient, we'll split it up into the quotient of two radicals. Are there questions so far? You guys are so quiet that sometimes I forget to stop and ask if you have questions because you're so quiet. And feel free also to use the raise hand feature if you have a question, but you feel like, oh, I'm not sure when the best time is to ask. So we're going to rewrite this as one fraction. And some of you will do this in fewer steps than others. But now I can say this is 9 plus 2x over 2x dx. And this is sort of a concept that you're going to use over and over again in this section, depending on how many exercises you end up seeing. So you will be able to use this again. And now we can split this up because remember, the radical of a quotient can be rewritten as the quotient of two radicals. And now once you see that, you'll note that the square root of 2x cancels out with the square root of 2x. And that leaves you with the square root of 9 plus 2x dx. Now, this is really similar to the integral that we just did from the quiz. Ours, I think, was 9x plus 1. So really similar. We're going to use a u substitution. We're going to let u be the radicand, 9 plus 2x. du will be 2 dx. Well, we don't have 2 dx's, we just have dx. So we have 1/2 du is equal to dx. And I am going to rewrite my limits of integration as u limits. My original limits were x limits from 1 to 3. If I know that u is 9 plus 2x, well, if x is 1, then I'm looking at 9 plus 2, which is 11. And if x is 3, 2 times 3 is 6, plus 9 is 15. So we'll be going from 11 to 15. So we're going to take 6 pi times the integral from 11 to 15. I'm going to put this 1/2 in front to represent that dx that I have. I need the 1/2 du. Then I'll have u to the 1/2 du. And then we'll integrate. Now everything's written in terms of u. There will be no back substitution done because we've already put everything in terms of u. And all we have to do now is use the FTC and complete the integration. So we'll have 3 pi times 2/3 u to the 3/2 from 11 to 15. The 3's are going to cancel. So now you have 2 pi times 15 to the 3/2 minus 11 to the 3/2. You can leave it like this. If there's something that can be simplified, like some sort of perfect square, like if it was, I don't know, 16 or 4 or something, in that case, you'd want to rewrite this in radical notation. The 3/2 power is just 1.5. So you could always rewrite it like this. You don't have to. This is a perfectly acceptable way of writing the same thing. So these area of a surface of revolution problems, like I said, there aren't a ton of them. just very few of them that you'll have to do. I just want you to get used to using the formula. It is slightly different from arc length just because you're multiplying by that function. So it kind of changes your integrand a little bit. But other than that, really the only thing happening. Switch over to my nighttime light. Okay. Okay. That was all I had to say about surface area. So I want to talk about work in 6.6. Any lingering questions on surface area? Okay, so the last section we're talking about is the section on work. There are a couple of different types of problems we're going to look at. There are some spring problems. There aren't going to be a whole ton of these, and they're pretty straightforward. They tend to be easy points on your test. So we'll do a couple of spring problems, and then we'll talk about pumping liquid from a container. I don't know why I really like those problems. I guess it's because I feel that they're so rewarding. But do remember that we're still in applications. And when we're talking about applications, we are going to be applying integration. So that's what you can expect here. 6.6 is work. It's actually all it's called is work. There's a lot of definition here, and I don't want you to get too bogged down in it. I'm going to give you just the most important things that you need to know. Work is done by a force on an object. So we define work with a W, and usually we say it's force times distance. If you've had physics, you've probably talked about work before in some form or another, depending on which physics class you've had. We're going to be talking about work, how it relates to springs, and for that we're going to be using Hooke's law, which again you've probably seen before. So Hooke's law is the force required to keep a spring in compressed or stretched position. Spring stretched or compressed position x units from equilibrium. So the equilibrium of a spring would be you're not stretching it out at all, you're not compressing it at all. It's where the spring sits on its own. And this force is a function of x, f of x equals kx. K is going to be spring constant. And then x is just the distance that your spring is moving. If k is, or I'm sorry, k is always positive. Sorry, I meant to say, I'm talking about the force sign. So k is always going to be positive. This measures the stiffness of the spring. A positive force is required to stretch the spring. The force is always in the direction of the displacement. So a positive force means that you're stretching the spring. So if you're thinking about this in the direction of the displacement, you're pulling the spring, I keep almost calling it a spring, you're pulling the string out. So the force would be positive. And then a negative force would be if you're compressing the spring. So, and that, the spring constant is going to be positive. So that force is going to be dependent on that x direction that you're taking your spring. So I'm going to give you an example on how to work on some of these spring problems. You're not going to see a whole lot of this. It's not super crazy or anything, but I want you to see it just because it's a very classic example of a work problem. Before I proceed, are there questions about Hooke's law? Okay. So I'm going to give you an example, and I'm going to give you a couple different parts to it. Suppose a force of 10 newtons Oh, and we should talk too about newtons. Sorry, I'm looking at I've combined a whole bunch of notes from so many times that I've taught Calc too, and I ended up overlooking that. When you're talking about newtons, a newton is kilogram meter per second squared, and it's a force. Newton. Let me tell you what it is. And we're going to be talking quite a bit about newtons today when we're measuring force. It is a kilogram meter per second squared. Usually they use a dash to say kilogram meter per second squared. You don't have to have the dash. It just sort of splits that up so it doesn't all look like it's combined together. And the way that we would measure work is in joules, which is a Newton meter, and that's a capital J. You've probably used these before. If you have not, you're learning about them now. A joule is a Newton meter. Is there anything else I forgot to tell you? I think we're good. Okay, so a Newton is a measure of force, and the piece of the Newton that's meters per second squared has to do with acceleration due to gravity. So that is dependent on wherever you are. If you're on Earth, you're going to be using the 9.8 value, which is the value we're going to be using today whenever we need to reference our force. Later on when we talk about like the density of water. We'll talk about that again. All right, suppose a force of 10 newtons is required to stretch a spring. Um, 0.1 meters from its equilibrium position. And hold it in that position. A, assuming the spring obeys Hooke's law, find the spring constant K. One more thing I wanted to add up here. It's driving me crazy, and I keep wanting to add it, and I can't find a good time to go back up here, so I'm just going to do it now. I wanted to note that this is a unit of force, the Newton, and the joule is a unit of work. I said it, but I want to make sure it's written down, because a lot of times what I say kind of gets lost in the shuffle when you're writing things down furiously. All right, so we are going to find the spring constant K, and we're going to use Hooke's law. So I gave you Hooke's law as the force equals Kx. So we're going to go ahead and use that with the information that we've been given. There's Hooke's law. You were given that there was a force of 10 newtons, and the spring was being stretched 0.1 meter from its equilibrium. So when you're solving for K, we're going to use the 10 newtons for the force. We're going to leave K as it is because we're trying to solve for the spring constant K. And X is the distance that the spring traveled. So it was stretched. So that force is positive. It's being stretched. We are moving 0.1 meters. So we're going to use 0.1 here. Now, if you were given something like centimeters, you would have to rewrite that in meters. Otherwise, you would not be able to work the same way with newtons, because remember that a joule is a Newton meter. We're talking about work here. So we want to have things written in terms of meters, not like centimeters or millimeters. And then we'll get to our constant by taking 10 and dividing it by 0.1. And 10 divided by 1/10 is 10 times 10, so you'll end up with K equals 100. And that's a spring constant, so it does not get a unit on it. And now that we found K, we're going to go ahead and write our force equation using that K. So now we can go ahead and use the fact that f of x equals kx as being f of x equals 100x. Technically, that's not what you were asked to find. You were only asked to find the spring constant, but we're going to refer to this in example B. Questions on A? B. How much work is needed to compress the spring 0.5 meters from its equilibrium position? So when we're talking about these spring problems, the way that we're going to find the work, because we already have an equation for the force, the work is given by the integral from A to B of the force. force, f of x dx. This is how we would find the work done by a spring. And the way that you're going to use this work equation is we're going to talk about starting at our equilibrium and then ending up somewhere else. Now, the information that I gave you was that we were compressing the spring. Remember, we said that if we're compressing, we're going in the opposite direction. X is going to be negative. So if I'm starting at the equilibrium, I'm starting at 0. So when I look for the work here, when I set up my integral, I'm going to start at the equilibrium. And if I'm compressing the spring, then I'm going to need to go away from the equilibrium in the opposite direction. So compression will be negative. So I need to take this not to 0.5, but to negative 0.5 because it's a compression. And then I'm going to use my force function that we already came up with in the previous piece of this problem, which is 100x dx. And we will integrate and use the FTC. So 100 divided by 2x squared, and we'll go from 0 to negative 0.5. By the way, you might notice at this point that maybe you were working on this and you forgot that a compression gives you a negative value for x, in this case for your upper limit of integration. You would still get the same answer if you used 0.5. However, it's really important that you use the correct sign because you're going to revisit problems like this later on in differential equations, and you're going to be doing different things with them using the Hooke's law model. So it's really important that you understand that even though your answer for the force will come out the same in this case, get into a good habit by using that negative sign for the compression. So our work is going to be 50 times negative 0.5 squared. And then when we take off that lower limit of integration, in this case, we don't need to worry about evaluating 0 because it's just a polynomial. And you should end up with 12.5. 50 times negative 0.5 squared is 12.5. And the work done is measured in joules. Okay. Questions on B? How much work is needed to stretch the spring 0.25 meters from its equilibrium? And you're going to use that same idea here to find the work. We're going to start at the equilibrium. We're going to stretch it 0.25 meters. And this will be a positive value since it's a stretch and not a compression. And we're still using that force function 100x. And integrating with respect to x. So you're going to get, same as last time, 50, this time 0.25 squared. And you should end up with 3.125 joules. And then the last part of this example, how much work is required to stretch the spring an additional 0.25 meters if it has already been stretched 0.1 meter from its equilibrium? Okay, so in the last two examples, we were starting at equilibrium. So when we were looking at our lower limit of integration, we started integrating at 0 because we were at the equilibrium. That's not the case in D. Our starting point now is not the equilibrium because our spring has already been stretched 0.1 meters from the equilibrium. So we're going to start at where it's already been stretched to, and then we're going to stretch it the additional 0.25 meters. So if it's already been stretched 0.1 and you're stretching it an additional 0.25, you're actually going up to 0.35 meters. And then everything else is the same, 100x dx. So you will again get 50x squared. And you'll take that from 0.1 to 0.35. And when you evaluate this using the FTC, you should get 5.625 joules. And you can kind of see from these numbers here that the work required to compress or stretch a spring is a pretty small value when it comes to joules. We're talking like single digit joules. This one's in the double digits. But there's not a whole ton of work required in this case to move our spring. Now, of course, it depends on how big the spring is and how stiff it is. Looking at that constant K. But we're going to get into these pumping fluid problems, and you're going to find that you're going to get these much larger values for joules for the amount of work that's being done, as you would imagine that you would. So that's the next type of exercise I wanted to go over with you. Let me give you a definition here on page 477. Before I move into that type of problem, are there any lingering spring questions? Like I said, there's not a whole ton to do with the springs. It's kind of a weird day just because we're kind of bopping around from, picking up these random topics here and there that we just have to finish out. Okay, so we're going to get into these like pumping liquid from a container problems. Sometimes this will be water, often it will be, not always. So the formula that you're given is that the work is the integral from A to B. Then you have rho, which represents density, times G, which is the gravitational constant, times A of X. I'm going to label all these before I give you an example so you know what everything is, times H minus X dx. You will probably find this formula to be incredibly helpful as you piece these together. So you might want to highlight it. It's very nice to have that laid out. I don't want you to think that this is always going to be in terms of X. A lot of times the way that you set this up might be different than the way I set it up. Most of the time, if I'm doing a pumping liquid problem, I actually use a dy integral, and I have an A of y and an H minus y, and I don't deal with any X's. But of course, you can interchange those. So rho is the mass density of the liquid, which you'll be given. G is the acceleration due to gravity. I'm trying to think if this ever won't be 9.8 meters per second squared. I'm pretty sure you're always going to be on Earth and you're always going to be working in metric. And as I just said that I'm looking at one problem where it's not. You will be told otherwise if that's not the case. I do include that information here. So G is the acceleration due to gravity. A of X is going to be the area function. The area function for a layer that is to be lifted. And I'm going to draw this out so you're going to get a really good idea of what that represents. H is the height the liquid is to be lifted above the bottom of the tank. And the liquid fills the container from X equals A to X equals B. You might want to note this is not a P. It looks like a P, but it's a rho. Most of you have seen this before. You'll probably be seeing it on the news soon as the new rho variant. I saw that we now have a mu variant, the coronavirus. Who knows? There'll be a rho variant eventually. everyone will become very familiar with their Greek alphabet. Okay, so I'm going to show you how this works. I'm going to give you an example. As long as you work these out methodically, filling out all these pieces, it shouldn't be some major guessing game. Just draw yourself a good figure. You'll be able to look at the region and determine what the area function is. You've done some work with that already, which should kind of have prepped you for this. But I don't want you to be like, oh my gosh, I don't know where to start. Start by drawing out a picture. Example 2. How much work is needed? To pump all the water out of a cylindrical tank with a height of 10 meters and a radius of 5 meters. The water is pumped to an outflow pipe 15 meters above the bottom of the tank. I know, this is one of those things where you read it and you immediately freak out. You're like, oh my gosh, this is terrible. The sky is falling. Everything's fine. Don't worry. I'm going to give you also here a value that you're going to be using anytime you're looking at water in this section. If you're looking at a different type of liquid, then you'll be given the density. The density of water rho, in this case, our rho. I'll just say rho equals, and this is going to be 1,000 kilograms per meter cubed. Now, the last thing I want you to be worrying about here is like, oh my gosh, I don't know rho and I don't know g. G is going to be 9.8 meters per second squared unless you are told otherwise. Rho for water is always going to be 1,000 kilograms per meters cubed. So when you're looking at rho times g, which you're going to need in your formula, remember that's the first thing that goes in here. You can already just state what that is, so you don't need to worry about it again. So rho times g is going to be 9,800, and it does not matter to me if you include the units, they're all going to pop out in the end anyway. But you're still going to have a kilogram. One of those meters is going to cancel out. 2 of them are going to stay. So you're going to have kilograms per meters squared second squared. Don't worry about the unit. The units will work themselves out. I don't like saying don't worry about the unit, but this is not physics, this is math. The units will work themselves out. The only time I would say worry about the units would be if I gave you a height of 10 centimeters or like 10 millimeters, you would need to rewrite that in terms of meters. That's when I would say worry about the units. All right, so here's the part we don't need to worry about. The rho times G, done. What I do need, though, is an area function and an H minus X. You're going to find, like I stated previously, we're going to actually use Y for this, just because we're pumping the water to the top of a tank. And to me, it makes most sense to set this up vertically if we're talking about pumping water and talking about bottom and top, so on and so forth. You're going to find that this is going to be easier. This is one of the few things that's going to be easier when you use dy. So we're going to draw a picture first of this situation. So let's see, you have a cylindrical tank. By the way, a cylindrical tank is the easiest kind to have because when you're talking about a cylinder, the sides are straight. And I will show you why that matters in a moment. But you can just draw this in 2D. It doesn't have to be any sort of 3D drawing. We know that the water is being pumped to an outflow pipe 15 meters above the bottom of the tank. I'm going to sit my bottom of the tank here on the x-axis. If you want to sort of make it look 3D, that's fine. I already did a terrible job making it look symmetric. I'm going to center it at the origin. I gave you the fact that the radius of this tank was 5 meters. So we'll let this be 5 to represent the radius. And I told you that the tank was 10 meters high. So it doesn't have to be exactly to scale, but 10 meters would be right about there. And it's a cylindrical tank. So it looks kind of like a can of soup. Like that. Now the problem says that you are pumping all of the water out of a cylindrical tank. So that assumes that your tank is full. What you're looking for here is you're taking all of it. It's going to an outflow pipe 15 meters above the bottom of the tank. So this will be at your 15 meter mark. And there's your outflow pipe. So what you're going to do here, in order to find your area function, A of y, it's very important that we get that. You're going to take a layer of water that's lifted. Now, I know that seems like a weird thing to do because we don't tend to think about water in layers because water is a fluid. But you're going to be thinking about this geometrically. So you are going to look at a layer of this of any thickness you'd like. Sort of like how we did these rectangles from when we were talking about volume. And then it doesn't matter. The thickness is going to be delta y. That's going to get taken care of when we integrate. What you need is the area of this layer. Now, if you're looking at a cylindrical tank, then that means that if you took a layer out of this, imagine if you were to look at this from the top of the tank, you were standing here, you were looking down, what you would see would be a circle. So the area of your layer is a circle. Because your region is a cylinder. You take this layer out, if you were to look down at it, it would be a circle. I know it looks like a rectangle from the front, but it's not. It's a circle. Any questions so far? So what we would need then would be an area function to represent the area of the circle. Now, remember that I said a cylinder is your best case scenario, and that's because no matter how thick you make this layer, the area of the surface is always going to be the same all the time because it's not like the sides are changing so that, you know, the circle would be bigger at the bottom, smaller at the top, or anything like that. I will give you an example like that next because I want you to see that too. But this circle will have the same area no matter where you move the layer. So you can scoot this layer all the way down and the circle will still have the same area because the sides are straight. So we could say that the area, our area function, is just going to be pi r squared, which is going to be pi times our radius is 5. I gave you the radius of the tank squared. So our area function actually is not really a function in y at all because it's a constant function, 25 pi. A lot of times this function will be a variable function. With a cylinder, it's not. So that's your area function. And then the last thing that you need, well, you need two more things technically for your integral, but you need h minus x. And remember, I defined h as the height from the bottom of the tank that the water is being lifted. So in this case, h is going to be 15 because we're lifting the water not just a full 10 feet, but 15 feet above the top of the tank. So I realized that the water sitting here at the top doesn't move the full 15. Doesn't matter. When you're using this formula, h is going to be the distance the water moves measured from the bottom of the tank. So h is going to be 15 in this case, measured from the bottom of the tank. And then the last thing you need are limits of integration. So if you want, you can start to put the rest of this integral together. The rho g we said was 9,800. So our work is going to be, we'll put that inside the integral if you want and move it out so it matches up. We're going from A to B. A to B, sorry, I'm losing my, I didn't actually define that. Oh, yes, I did. Liquid fills the container from x equals A to x equals B. Remember, we were pumping all the water out of a tank. So that assumes that your tank is full. So we're going to be lifting all the water out wherever the water actually exists. So we're going to go from 0 all the way up to 10. So this is just where we actually have water existing in the tank. So don't take it all the way up to 15 because you don't have any tank space between 10 and 15. The water is being housed in the tank. The tank is full from 0 to 10. Then we have the rho g. The rho g is 9,800. Let me get my formula back up here. Then we have your area function, which we found to be 25 pi. That part goes right here. And then we include h minus x, which in our case is going to be h minus y because we're moving our water vertically. As long as your layer is horizontal, you're moving this layer up vertically. That's why we have the dy integral. And I feel like that's pretty intuitive, but I just want to make that clear as to why we have a dy instead of a dx. I mean, technically, I can't force you to write y. Everything can just look funny in terms of x, but technically it's moving up to an outflow pipe. And then you're just going to integrate. You're going to have 9,800 times 25 pi, and then you'll have 15y minus 1/2 y squared, and you'll take that from 0 to 10. And when you integrate this, you will get, and oh, by the way, sometimes I'll ask for your answer in terms of pi. You might be asked for both. In terms of pi, this would be 245. No, I missed a comma here. 24,500,000 pi joules. That would be the exact answer. And if you approximated this and multiplied by pi, you would get 7.697 times 10 to the 7th joules. By the way, remember that when your calculator lists something like 10 to the 7th, it's going to do that with that little E symbol. So if you were to actually take, seriously, 24,500, 1, 2, 3 times pi 6. Your calculator will actually give you this. So you're going to have to put that in scientific notation yourself. 76969020. I don't know how it's going to ask for your answer. It might ask for it exact. Or it might give you the times 10 to the something, and you might have to fill in the exponent, because these are going to be pretty big numbers for work. So your exact value is this one, and the approximated one multiplies it by pi, and you tricate off the decimals. So I want to do one more of these where your area is variable. Are there any questions here? Oh, actually, I forgot. Just to give you a little bit of practice working around these, I was going to ask you, I was going to have us switch these integrals up. How do we want to write this? Okay. For example 2, what if, and let's say A, you were only emptying the top half of the tank. Only the top half of the tank is emptied. So I want you to get really familiar with which parts of the integral are doing what here. Now, when we did this example, in example 2, we said that we were emptying all of the water out of the tank. And we were emptying all of the water out. When we did that, we were integrating from 0 to 10 because the whole tank was full of water. However, if you're only emptying half the water out of the tank, you're going to only be lifting the top part of the water out. So just whatever's in the top half of the tank. So instead of going from 0 to 10, you would set up your integral to go from 5 to 10. And you would still have rho g times whatever we had, 25 pi. That's not going to change. And then the other thing that could possibly change, but it's not going to in this case, would be h. In this case, we're emptying the top half of the tank. That only affects how much water is coming out. So that only affects your upper and lower limits of integration. But you're still emptying it to an outflow pipe 15 meters above the bottom of the tank. So we would still use 15 minus y in our integral. So that's one way that your integral could slightly change if the information changed. Another thing that could happen would be if the tank is half full, work to empty the tank if it's only half full. So this is another place where having that picture is going to make such a huge difference for you. So if your tank is only half full and you're trying to empty it, well, if it's only half full, that means that you only have water in the tank from 0 up to 5. If you only have water from 0 to 5, then if you're emptying the whole tank, you're only going to be emptying the water that is in the tank. So you're only going to integrate from 0 to 5. But note that I didn't say anything about switching the outflow pipe. So everything else will stay the same. Questions on A or B? C, what about the work required to empty the tank if the outflow pipe is at the top of the tank? So what if you are emptying the tank with the outflow pipe at the top of the tank?
So you're saying the top of the tank versus the 15, right?
Yes. So so it might be like, wait a second, I thought the outflow pipe already was at the top of the tank. Well, technically it's above the tank, but it's not at the top of the tank. So that picture would look slightly different if you were thinking about your cylinder. Your outflow pipe instead would be right here at the 10-meter mark. Right there at the top of the tank, there'd be like a spout where that water would be getting pumped out. So the difference there is that you would still have a full tank of water. That hasn't changed based on the original example. So I'm just taking the original example and just sort of changing the information in these parts. So we're still pumping all the water out, and it still has water in it from 0 to 10. The radius is not changing because that has not moved at all. The difference would be in the height. So you are now looking at a height that's 10 meters above the bottom of the tank, not 15. Okay, so I have good news and bad news. The good news is I'm going to let you go 5 minutes early. The bad news is I won't get to finish my example, so I'm going to have to do it asynchronously, but it's going to be short. And you know what? I actually really wanted to do 2 more examples. I think it'll be more helpful to you if I do 2. So I will do those asynchronously. So if you are looking for more work examples, which you absolutely should be, because only looking at one cylinder is not really going to help you that much with your homework, because you need to worry about that area being some sort of variable function. I'll record that for you. And since it's going to be short, I'll probably do it tonight. Maybe I'll just do it right now if no one sticks around for office hour. Otherwise, I'll do it after. But yes, I do want to give you a little bit more so that you have some more to reference while you're working through your homework. But I'm going to assign some homework for you with some of these tank problems, and there might be a spring problem here and there to sort of get you ready for what you have to do for your test in 6-6. So expect maybe like 1 tank problem, a spring problem, which will be like easy points for you. Other than that, I will send out an email letting you know when I'm going to include some extra student time over the weekend, since you won't have very much asynchronous stuff to do. I mean, it's going to be maybe like, you know how I drag out examples. It'll probably be like 40 minutes by the time I'm done. But it will be like 2. I'm going to give you like 2 examples asynchronously. That's it. I don't have a ton more to do. And then if you have questions, you can let me know. I will be on until 8:30 for the office hour. If you want to stick around, other than that, just check your email for information about next week and get on that homework. Some of you are really behind, so you got to catch up. Test is a week from tonight. That is all. Have a wonderful evening, you guys. Bye-bye.
I have a quick question.
Sure.
Those 3 problems we went over earlier, you said you were going to extend the 6-3 homework so I can enter them?
Yes.